Lie algebras, problem session 2, structures. Problem 1. Let A be the Lie algebra with bases H, E1, E2, and E3, and the Lie bracket given as follows. The bracket of any EI with any EJ is 0, and the bracket of H with EI is equal to IEI. So here, any I and any j is from 1, 2, and 3. Determine whether A is nilpotent or and solvable. Solution. Let us start with computing the Lie bracket of A with itself. From the definition, we see that in the outcome, we can get any EI with some non-zero coefficient. So the Lie bracket of A with itself is a linear span of E1, E2, and E3. Again, from the definition, we see that if we now take the Lie bracket of the Lie bracket of A with itself, it will be 0, because the Lie bracket of any EI with any EJ is 0. And this literally means that our Lie algebra A is solvable. On the other hand, if we take the Lie bracket of A with the Lie bracket of A and A, we will get the linear span of E1, E2, and E3. This is because H is in A, and all EIs are in the commutant of A. In other words, taking the bracket of A with the bracket of A and A is equal to the bracket of A and A. And by induction, if we iterate this process, we see that the bracket of A with the bracket of A with the bracket of A and A is still equal to the bracket of A and A. And so on. This means that in this sequence we will never get any zero spaces, which means that our Lie algebra A is not nilpotent. This completes solution of problem 1. Problem 2. Classify simple finite-dimensional modules over the Lie algebra A from the previous problem. So this is a Lie algebra with the bases H, E1, E2, and E3, where the bracket of any EI with any EJ is 0, and H bracketing with EI is equal to IEI. Solution. As we already established in problem 1, this algebra is solvable, so we can apply Lie's theorem and have that each simple finite-dimensional module over this algebra has dimension 1. Let V be a one-dimensional A module. The associative algebra of all linear transformations of a one-dimensional vector space is commutative, which means that the bracket of A and A, the commutant of A, annihilates V. Next, we observe that A, quotient by the Lie bracket of A with itself, is a one-dimensional space with the obvious basis given by the class of the remaining element A. So the bracket of A and A is spanned by E1, E2, and E3. When we factor them out, the only thing which remains is H. The module V is completely determined by the action of H on it. Since V is one-dimensional, H acts on V as some scalar, let's say lambda. Clearly, each scalar lambda defines a simple module. So if you take a one-dimensional vector space and we say that H acts on it as lambda and E1, E2, and E3 act on it as 0, this of course defines a one-dimensional A module, which we denote by V lambda. Two such modules are isomorphic if and only if the corresponding parameters lambda are the same. For different lambda, we will get non-isomorphic modules, because our lambda is the eigenvalue of H, and in isomorphic modules the eigenvalues should be the same. Therefore, simple finite-dimensional A modules are in bijection with complex numbers, up to isomorphism of course. For the complex number lambda, we have the module V lambda, on which H acts as lambda, and E1, E2, and E3 act as 0. And this completes problem 2. Problem 3. Determine the matrix of the Killing form of the Lie algebra A from problem 1. So that's a Lie algebra with the bases h, e1, e2, and e3, ei and ej bracket to 0, and h bracket with ei is ei. Solution: we solve this problem by brute force, that is, by computing all involved matrices. The matrix of the adjoint operator add h in our basis is the diagonal matrix, where we have 0, 1, 2, and 3 on the diagonal. This is because the bracket of h and h is 0. The bracket of h and e1 is 1 times e1, so we have 1 on the diagonal. The bracket of h and e2 is 2 times e2, so we have 2 on the main diagonal, and so on. The matrix of the adjoint operator for e1 in our basis is the following matrix, where we have zeros in columns 2, 3, and 4, and the first column is 0, minus 1, 0, 0. This is because e1 bracket with h is equal to minus e1, while its bracket with any ej is 0. Similarly, the matrix of the adjoint operator for e2 is a matrix where in the first column we have 0, 0, minus 2, 0, and the rest is 0. And the matrix for the adjoint operator of e3 has 0, 0, 0, minus 3 in the first column, and the rest is 0. Note that the value of the Killing form on a pair of elements x and y of a Lie algebra is defined as the trace of the composition of the linear operators add x and add y. And we have already computed the matrices for all the adjoint linear operators for our basis. So we note that the trace is the sum of all diagonal elements in a matrix. All matrices which we have, which we computed, they all are lower triangular, and except for the adjoint matrix for H, which is diagonal, all the remaining matrices are strictly lower triangular. So if we multiply a strictly lower triangular matrix with a lower triangular matrix, we will get a strictly lower triangular matrix, which means that on the diagonal there we will have zeros, so the trace will be 0. So the only chance to get a non-zero element somewhere on the diagonal in our product add x times add y is to multiply add h with itself. This means that in the matrix of the Killing form we will have all zeros except for the position 1, 1, where we have the trace of the square of add h. And when we square a diagonal matrix, on the diagonal we just have the square, so we'll have 0, 1, 4, and 9, and the sum of these is 14. So the answer is the matrix where we have 14 in the position 1, 1, and the rest is 0. Problem 4. Let B be the Lie subalgebra of SL2 spanned by H and E. Construct an example of an infinite-dimensional simple B module. Solution. Recall that the Lie bracket in B is given by the bracket of H and E is equal to 2E. So the universal enveloping algebra U of B is the quotient of the free associative algebra on the generators H and E by the relation that HE minus EH is equal to 2E. Recall that this universal enveloping algebra has a PBW basis, which has the form h to the power I times e to the power j, where I and j are non-negative integers. Let I be the left ideal of the universal enveloping algebra generated by the element e minus 1. Denote by m the quotient of the universal enveloping algebra by this left ideal. Then this quotient is clearly a module over UB, because we have a module and we factor out a submodule. A left ideal is a submodule. We also know that this quotient is clearly non-zero, as we can see from the PBW basis. If on the right we evaluate e to 1, we get arbitrary polynomials in H as the outcome. So now we claim that the module M is simple, and this will complete the solution to our problem, because we know that B is solvable, and so by Lie's theorem all simple finite-dimensional B modules must have dimension 1. And on all such modules, the commutant of B with itself must act as 0, and this computant contains the element E, but by construction in our module, the canonical generator, which is just the image of the identity element, E acts on this canonical generator as 1 by definition, because E minus 1 annihilates it. And so E does not annihilate our module. This means that our module, if it is simple, it cannot be finite dimensional. It will automatically be infinite dimensional. So to prove that our module M is simple, we know that, of course, it is generated by the element V, by the image of the identity in our quotient. That's because U of B is generated by the identity. Since E times V is equal to V by definition, it follows from our PW basis that M is equal to the application of the universal enveloping algebra of H, which is the same as the polynomial algebra of H to V. Because in our basis, any element is H to some power times E to some power, and if we delete all the powers of E, what remains is H, and nothing more. So let alpha of H be some polynomial in H of strictly positive degree. From the bracket relation that H bracket with E is equal to 2E, we have the following relation. So this is just, we are rewriting the bracket relations that E times H is equal to H minus 2 times E. So we can move E from left to right past H at the expense of subtracting 2 from each H. Therefore, E times alpha of HV is equal to alpha of H minus 2 times EV, and this is equal to alpha of H minus 2V. So we move E through any polynomial in H, and the expense is that we subtract 2 from each occurrence of H. So we get the same polynomial, but evaluated at H minus 2. So now we start from the element alpha of HV. So using the action of E, we get the element alpha of H minus 2V. The difference between alpha of H and alpha evaluated at H minus 2 is a non-zero polynomial in H whose degree is exactly 1 smaller than the degree of alpha. This means that application of E several times will give us a scalar polynomial. And this is exactly the canonical generator of M up to some non-zero scalar. And this shows that the module M is generated by any non-zero element, and hence is a simple module. This completes problem 4. Problem 5. Let B be the Lie subalgebra of SL2 spanned by H and E. Classify all Cartan subalgebras and regular elements in B. Solution. Recall that the Lie bracket in our algebra B is given by the bracket of H and E is equal to 2E. Let us take an arbitrary element in B. So we can write such an element as x times H plus y times E, where x and y are complex numbers. Then the matrix of the adjoint linear operator on B for this element is as follows. So that's a matrix 0, 0, minus 2y, 2x. If we apply the adjoint operator of xh plus ye to h, the first term cancels, and the second term gives us minus 2ye. And if we apply it to e, the second term cancels, and the first term gives us 2x. The characteristic polynomial for this matrix, that's a lower triangular matrix, so the characteristic polynomial is just subtract lambda on the main diagonal and take the product. We will get minus lambda times 2x minus lambda. So it is the polynomial lambda squared minus 2x lambda. And this element is regular if and only if we have the smallest possible degree of lambda appearing with a non-zero coefficient. And the coefficient is 2x. So this element is regular if and only if x is non-zero. We just proved that the element xh plus ye is regular if and only if x is not 0. We have classified all regular elements in B. Now about Cartan subalgebras. Note that the commutant of B with itself is the linear span of E. That's by definition. And now if we try to take a commutant with B once again, we will again get the linear span of E, because H belongs to B and E belongs to the commutant, and so on. So this will never get 0, so our algebra B is not nilpotent. So our algebra B is not its own Cartan subalgebra. But B has dimension 2, so any Cartan subalgebra of B therefore must have dimension 1. A Cartan subalgebra is a subalgebra which is nilpotent and self-normalizing. If we take any subalgebra of dimension 1, it is abelian and hence nilpotent. So any subalgebra of dimension 1 is nilpotent. The question is when it's a Cartan subalgebra, if and only if it is self-normalizing. So in order to satisfy the self-normalization condition, the normalizer cannot be bigger than the subalgebra. And the only thing which is bigger is the whole algebra. So to ensure self-normalization, we need the condition that the normalizer is not the whole algebra. So if we bracket B with our linear span of our one-dimensional subalgebra generated by V, we cannot get inside the linear span of V. If the element V is in the linear span of E, then of course the commutant of B with it is inside the linear span of CE. And so our self-normalization condition fails. So the elements V which are in the linear span of E, they do not span Cartan subalgebras. On the other hand, if V is outside the linear span of E, then the bracket of B with CV is equal to CE, and this is definitely not inside CV because V is not in the linear span of E. So our self-normalization condition is satisfied. This means that Cartan subalgebras are exactly the one-dimensional subalgebras spanned by elements V, which are outside the linear span of E. Each such subalgebra contains a unique vector of the form H plus XE, where X is some complex number. So Cartan subalgebras are classified by such vectors. And this completes problem 5. Problem 6. Classify all Lie subalgebras of SL3, which contain the subalgebra of all non-strictly upper triangular matrices. Let us denote by B the Lie subalgebra of SL3 consisting of all non-strictly upper triangular matrices. This subalgebra is usually called the Borel subalgebra of SL3, or the standard Borel subalgebra of SL3. Let P be a subalgebra of SL3 which contains this Borel subalgebra. There are two obvious choices for P. We can take as P the Borel subalgebra itself, or the whole algebra SL3. So there are two obvious choices. Let's take them out and assume that our subalgebra P is not B and is not SL3. Since P contains the Borel and is different from the Borel, the algebra P must contain a non-zero linear combination of the remaining basis vectors in SL3, and these are the matrix units E21, E31, and E32. Let us denote by H the element E11 minus E22. It's an element of B, in particular it's an element of P. Note that the Lie bracket of H with E21 is minus 2 E21. The Lie bracket of H with E32 is E32, and the Lie bracket of H with E31 is minus E31, which means that our matrix units are the eigenvectors for the adjoint operation of H, and they correspond to different eigenvalues. And if you have a linear combination of three eigenvectors with different eigenvalues, then we can use the adjoint operator to single out these eigenvectors from any non-trivial linear combination. So as soon as one of them appears with a non-zero coefficient in a linear combination, we can single this vector out using the action of H. In other words, our subalgebra P contains one of the matrix units E21, E31, or E32. If P contains E31, then we can take the Lie bracket of E31 with E23, and this gives us E21. So E21 should be in P. If P contains E31, we can also take the Lie bracket with E12, and we get E32. So this is also in P. And then P is the whole of SL3 because it contains B and the three additional basis elements. That's a contradiction to our assumption that P is different from SL3. So P cannot contain E31. Further, if P contains both E21 and E32, it contains the Lie bracket, which is E31. And this is a contradiction by the previous slide, which means that P can contain either E21 or E32, but not both at the same time. And this means that P is either the Borel plus the linear span of E21, or P is the Borel plus the linear span of E32. And of course, both these are subalgebras. So as the answer, we have exactly 4 subalgebras which satisfy our condition. And these are the subalgebras consisting of the elements which fit in the following 4 shapes. This is the Borel, and the rightmost is the whole of SL3. This is the Borel plus the linear span of E21, and this is the Borel plus the linear span of E32. And that's complete the solution of problem 6. Thank you very much. Hope you enjoyed this problem session, and see you next